Hi everyone, my name is Yiming Zhou, and I received my PhD in Electrical and Computer Engineering from UCLA under the supervision of Professor Jalali. In this series of video, I will present my PhD dissertation on the topic Vision Enhancement and Artificial Intelligence via efficient and interpretable algorithms inspired by optical physics. This is the outline of my full presentation. I will start with the background and motivation of my research and then give a brief overview on the three main topics of my dissertation. In the first topic, I will focus on the optical physics side, introducing photonic time stretch, which is a hardware technique originated from our lab and seeded the inspirations for the algorithm development later. In the second topic, I will focus on the computational imaging part, introducing a new class of physics-inspired computer vision algorithms called PhCV. In the third topic, I will focus on the AI part, presenting a novel physics-based trainable model called nonlinear Schrödinger network. In this video, I will cover the background and motivation along with the dissertation overview. The Antikythera mechanism from ancient Greek is one of humanity's first attempts at analog computing. This ancient machine can calculate the positions of the sun and moon as a function of date and time. Since then, several generations of computing machines were built. Invented in 1206, Castle clock was a hydro-powered mechanical clock, and it was among one of the first programmable analog computers. Later during the Industrial Revolution, tide predicting machine was invented as an analog computer to predict the tides at specific locations using harmonic analysis. These analog computing devices in early days performed computational tasks by mapping them into proxy mechanisms that mimic the problem of interest. Later on, with the development of more predictable and governable digital devices, analog computers were replaced by general-purpose digital computers. With powerful CPUs and GPUs, digital computers are highly successful in following any instructions coded in software. Nowadays, thousands of digital computers are clustered into gigantic data centers that support our modern society by performing computations endlessly. The ever-growing computational power has led to the thriving progress of artificial intelligence, particularly deep learning. AI models have demonstrated remarkable success, especially in computer vision and natural language processing. Nowadays, large language models like ChatGPT and Claude, along with image generation tools like Midjourney, have opened up a new chapter of generative AI. However, the success of AI comes with challenges and limitations. The first challenge is the expensive computational and memory cost. The computing power nowadays struggles to keep pace with the demands of AI training and inference, leading to substantial power dissipation and monetary costs. Another significant challenge is the limited interpretability. The highly nonlinear and complex nature makes it difficult to understand how neural networks arrive at their predictions. Moreover, the reliance on large-scale datasets can be a significant barrier in domains where data acquisition is costly or restricted by privacy concerns. All of these issues demand fresh ideas or for more efficient and interpretable computing systems and algorithms. To get some insights of how to solve these challenges, let's look at the evolution of science. In early days, before we had accurate instruments and advanced mathematical tools, science was deduced from trial and error by an alchemist. It was all empirical and data-driven. Then we entered the era of physics, where we began to develop deterministic models based on first principle that using only a few quantifiable parameters, such as mass, charge, and distance. These models can explain a vast number of phenomena. Nowadays, AI models leverage billions or even trillions of trainable parameters to learn from large-scale datasets. Again, it becomes empirical and data-driven. Given this spiral rise, we believe that a new paradigm called physics-AI symbiosis could be a promising solution to existing limitations of AI. In this new paradigm, scientific and data-driven models are integrated in a synergistic manner to extend the capabilities of both. A lot of attempts have been made to integrate physics with AI. For example, physics laws can be blended into the design of neural networks to solve partial differential equations more efficiently. On the other hand, physical systems can act as hardware accelerators to perform specialized computations, such as using metamaterial to perform math operations, using free space optics for neural network inference, and using nonlinear optics to perform transformations on spectrally modulated optical data. In my dissertation, I will focus on a new direction called physics-inspired algorithms that falls into the general physics AI symbiosis category, but it is different from existing approaches. Physics-inspired algorithms leverage laws in the physical world as blueprints to craft algorithms in the digital domain. Such algorithms have several benefits. First, because physics rules are usually succinct, physics-inspired algorithms feature low dimensionality, which further leads to high efficiency during runtime. Also, it is fully interpretable as you can trace back to the original physics model. It is not like traditional algorithms that consist of handcrafted empirical rules. It is not like deep learning that is computationally heavy and has limited interpretability. It is also not analog computing, where the flexibility is restricted by physical hardware implementations. As an overview of my dissertation, it has 3 parts. In part 1, I will start with the principles of photonic time stretch, a hardware technique rooted in optical physics for ultra-fast and single-shot data acquisition. I will describe the physical and mathematical model of it and show how it seeds the idea of developing algorithms. Then, in part 2, I will introduce a new class of algorithms for image and video processing, called PhD, and focus on its remarkable success in vision enhancement tasks. Finally, in part 3, I will introduce a novel physics-based trainable model called nonlinear Schrödinger network. It treats the partial differential equation as a numerical model to learn complex patterns from data, and is more interpretable and parameter efficient compared to black box neural networks. This leads to the end of the first video. In the next video, I will cover part 1, a unified framework for photonic time stretch systems. Thank you.